The second kind of FRQ on your AP Physics exam is called translation between representations. And this one has the most marks of any of the questions. So you could say it's the most important. In this video, I'm going to do a full breakdown of one question and show you what the key ideas are and the structure that every single question like this will have. This is called translation between representations, so we should ask, what's a representation? In physics, we have all these ideas and equations and pictures, and sometimes we use representations to talk about information. These representations are helping us to understand what's going on in the different lenses. There's a few representations that you should be familiar with, and maybe you didn't know they were called representations, but maybe you know what they are. They include a free body diagram, a graph about motion, velocity, or acceleration, or an energy bar graph. The question that we're about to look at actually has all three of these kinds of representations, and you'll get familiar with how to do them and use them. This question is worth 12 marks, so it's the biggest of all the FRQs. The others are worth 10 or 8 marks. And this question has 4 parts, and every question will follow the same 4 parts. In part A, they'll ask you to create a representation. So there might be a graph that you need to draw or create. In the second part, you're actually going to need to derive a mathematical formula. So part B isn't actually about representations, it's about the math routine side. In part C, they're going to ask you to draw or sketch a graph. And in part D, they'll ask you to do another thing to do with representations. In this question, what they do is they have a student's, in this question, part D has a representation that you need to critique, whether it's good or bad. So let's go through this question to see how it works. I'm going to begin by reading it. This question comes from the sample exam. A block of mass M is attached to an ideal spring, whose other end is fixed to a wall. The block is displaced a distance x0 to the left of the spring's equilibrium position as shown in figure 1. The block is then released from rest and oscillates with negligible friction along the horizontal surface. While the block is oscillating, it has maximum speed, Vmax. The energy bar charts in figure 2 represent the spring potential energy US of the block spring system and the kinetic energy of the block as the block passes through the positions x equals x0, x equals 0, x equals x plus, while the block oscillates. The bar chart at x equals negative x0 is complete. Draw shaded rectangles to complete the energy bar charts in figure 2 for positions x equals 0 and x equals plus positive 0. So the first thing to do in any FRQ is to identify what are we talking about, what part of physics are we doing. So here we're looking at oscillations or a simple harmonic oscillation. So there's a block on a spring, so we have a spring oscillator. And in this first question, we need to create a representation, in this case an energy bar graph. There are 3 positions that we care about for this block, and there are 3 energy bar graphs that go with that. Now, when we think about oscillations, energy is a really helpful way to think about it. When the block is at x equals negative x0, it's going to have full extension of the spring, and there we'll have spring energy. When the block is in the middle, x equals 0, then it's going to have no spring energy, it's just going to have kinetic energy. So the spring compression is 0, the spring energy is 0, and all the energy is kinetic energy. Because of the conservation of energy, we can say that the amount of energy that is spring energy will be 100% converted to kinetic energy. And then when the block is on the far side, where x equals x positive 0, then it's going to have, again, just spring energy. The velocity will be 0 there, and it will have just spring energy. This compression is full. So this is an oscillator, and it's oscillating between spring energy and kinetic energy. So we can represent on the bar graph. Here is what the energy bar graph looks like. They've given us the first one, and they're saying that the energy is totally spring energy and kinetic energy is 0. We always have to do a little line at 0. If an energy is 0, we've got to say energy is 0. We draw that little line there. So when we think about x as negative x, that's on the far left side, all the energy is spring energy and there's no kinetic energy. when we draw a bar graph for the middle position where x equals 0, we're going to say here all the energy is kinetic energy and none of the energy is spring energy. For spring energy, I'm going to draw a little flat line, just like that. There's no spring energy. And for the kinetic energy, I'm going to draw a bar. And the key thing is I want to draw the same height as the spring energy in the first graph. So there's 3 lines, so it's 3 lines high. So I also need to draw 3 lines high for the kinetic energy here. There we go. So now I need to do the energy bar graph for position on the other side where x equals positive x naught. So here, velocity is 0, kinetic energy is 0, and it's 100% spring energy. Just like that. Again, I need to make sure to put a little dash there for the kinetic energy, and I need to put 3 units high for the spring energy. This representation is worth 3 marks of the 12 marks. So I just want to pause for a second. I want to say something. On my website, I have a document about how to do FRQs. If you click the link below, you can go to my website and get a full guide about all 4 kinds of FRQs. So what we did was we created a representation, in this case an energy bar graph. Let's read question B. Figure 3 shows the position of the block as a function of time. Figure 4 shows the force exerted by the spring on the block as a function of time. And you can see those graphs there. And just notice for the position, it starts with negative x naught, and that's the position on the left. And at that time, the force is positive F max. So we'll just draw a free body diagram here. When we think about oscillating questions, we just got to think carefully about direction. So at time is 0, the block is at the far left there. Define this as negative x, which is why it's negative in the position graph, but the force is pointing to the right. So that force is a positive force. Anything pointing to the right is positive. If we draw the free body diagram on the other side, where x is x positive, the force is going to be pointing to the left. So here, at x equals positive x naught, the force is pointing to the left, so we draw that as a negative force. And that's at time is t naught, the time it took to go from the left side to the right side. But the position, that's positive. So we draw that as a positive x there. And what about in the middle at half t naught? Here, there is no force of spring, so that's 0, and also the position is 0. So at t equals half t naught, both the position and the force are 0. So the x is traveling between negative to positive in the first t, from 0 to t naught, and the force is traveling from positive to negative. And you can see that on the graph. Okay, I just wanted to go over that. Part B says this. Using figures 3 and 4, determine an expression for the spring constant of the spring. So here in B, we're actually going to do some mathematical routines. And for determine, we just have to write something down. To define the spring constant, we remember Hooke's law. The force of a spring equals the k times x, spring constant times x. So they want us to find the k. So the f here is they've defined x max, and the x is they define x naught. So that's it. So that's 1 mark. We have an expression of k equals f max divided by x naught. Part 2 says this. Starting with an equation for the period of a mass of a spring, derive an expression for the mass of the block. Express your answer in terms of t naught, x naught, f max, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. When I started doing this question, I did it wrong. I started thinking about the conservation of energy, and I said spring energy equals kinetic energy. And you get something, but it's not what the question is asking us to do. It says start with a different equation, the oscillation period for a spring. So whenever there's a derived question, you always get 1 mark for simply writing down a fundamental principle, like they say. So here, the formula is the period formula. So this question is 3 marks, and we get 1 mark by just writing that thing down. So we're trying to solve this for the mass. So let's square both sides. Okay, and now we need to solve for the mass. Move k over n 4 pi squared. So far, so good. T squared k over 4 pi squared is the mass. Now, I'm not quite done. I need to say a couple of things. they want us to write it in terms of T naught, X naught, and F max. So the period is not quite the same as T naught. If you look on the graph, you'll see T naught is the time it takes to go from the left side to the right side. So the period is going to be that 2 times. And we have an expression for the spring constant. K is F max divided by X naught. So to get this question fully correct, I need to take these two and plug them into my expression of M that I have. Now I just have to do a little simplification. I'm going to square the stuff in the brackets, move the X naught to the bottom, and I can cancel the number 4. And that's an expression for the mass. The mass is T naught squared times F max divided by pi squared times X naught on the bottom. Now that feels kind of weird, but this is what we're doing in AP Physics, using a mathematical routine to come up with an expression. And again, a determined question, we can just write it down for 1 mark, but a derived question is going to be several steps, beginning by writing down a fundamental principle for 3 marks. Okay, so that was 4 marks together for 1 and 2. Now we're going to move on to part C. On the axes provided in figure 5, sketch a graph of the velocity of the block as a function of time. So they gave us graphs as X and F max as a function of time, and now we need to draw a graph for the velocity as a function of time. So maybe I'll just draw again the picture and we can think about it that way. So there's 3 positions for the block. X equals negative X naught, X equals 0, and X is positive X naught. So what's the times? This is time is 0. This is time T naught. So this here is going to be, the first time it comes across, half T naught. So what's going on with the velocity? At the very beginning, here, the spring is only having spring energy and there's no kinetic energy. The velocity is going to be 0 there. Here, the velocity is max, and it's pointing to the right, and we said right is positive. Here at time equals T naught, velocity again is going to be 0 because we're having spring energy, not kinetic energy. So I'm going to take these 3 points and plot them on the graph now. So starting with here, at time is T naught, the velocity is 0. At time is half T naught, we have V max. At time is T naught, we have V is 0 again. So what's going to happen is the next half is going to go to negative. That's where it's traveling this way with V max here. So we're going to have to put V as negative V max as 1.5 T naught. And now we just plot the rest of the points on there. And there you go. So this looks like a sine graph. So this is the kind of graph we should be normally doing in an oscillation chapter study. This graph is actually worth 3 marks, and we want to make sure we do a couple things right. We start the velocity at 0, at time is 0, and it goes positive, so then the first one at half t is V max. It's important that we keep the period the same. So the period is 2 T naught, so it goes from the beginning back to the beginning at 2 T naught. Okay, in part C, we sketched a graph, and now we're going to finish with part D. A student sketches the free body diagram in figure 6 and makes the following claim. The free body diagram shows the forces exerted on the block at time equals 1.5 T naught. Justify why the student's sketch, figure 6, and claim are or are not consistent with the velocity graph of time you sketched in part C. So we see a free body diagram there, and we have to say, is this right or not? So what time is 1.5 T naught? So here are the first 3 positions again. Time is 0, time in 1/2 T naught, time is T naught. So 1.5 T naught is going to be in the middle again, when the velocity is to the left, maximally to the left. So what's going on here is we're all in kinetic energy. The compression is 0. Remember, Hooke's law says that force equals kx, or negative kx. It's okay. the main idea is that the force is going to be 0 here. So we can say that this free body diagram is wrong. When time is 1.5 t naught, the force is going to be 0. However, this question asks us to justify it with reference to what we sketched in part C. So if you remember, what did we say at that part C? That's part of the sine graph. And what's going on with the velocity graph at part C is that the velocity is Vmax negative. And we could look at it and say the slope of that graph is 0. And because the change in velocity, the slope in velocity is 0, that means that the acceleration is 0. And if the acceleration is 0, that means the force is going to be 0. Therefore, this is wrong. Let me read the example question answer that they give in their solution. The claim and free body diagram are not consistent with my graph of velocity as a function of time. At time t equals 1.5 t naught, my velocity graph is at a minimum and the slope of the velocity graph at that time is 0. This means that at t equals 1.5 t naught, the acceleration is 0, and because acceleration is directly related to force, the force from the spring should be 0 at t equals 1.5 t naught. Okay, we're done the 12-mark FRQ. Good work. Now you're equipped to get 12 marks on the biggest FRQ. Good for you.